Hi guys, welcome back to the channel. As per usual, just a couple housekeeping things to get started. This video is sponsored by Digilent. Thank you very much. They did provide the license to the software you're about to see. And of course, all thoughts and opinions expressed in this video are my own and do not reflect those of any company I am currently or have previously been associated with. So, now that everybody's happy, roll the intro. So I had somebody ask me an interesting question the other day, in that because I'm an electronics engineer specializing in FPGA firmware development, and I have a lot of custom hardware, or just hardware in general, I need to interface with, how do I do that remotely? And I realized the answer to that I've been taking for granted because it seems second nature to me. But the more I thought about it, I thought it would be great to make a video for you guys to kind of show you some of these tools that I've been using pretty much my entire career that make life a lot easier, not only if I'm remotely, but just to automate a lot of my daily life, especially when I get into that part of the development cycle where I'm further in, so some of the beginning steps I don't need to explicitly do. So this video is going to be all about how to create a setup, a benchtop setup that is controllable from a remote PC, as well as a setup that you can automate to run a full sequence of tests rather than individually pressing buttons on all of your test equipment. So let's get into that. So when creating a benchtop setup that you can control remotely, the first place to start with is the hardware. So taking your target device that you want to test and control, or your DUT, you need to figure out how to provide it stimulus, provide it power, and then measure any of its outputs, any of its desired outputs that you want. Based on that, you need to have some form of instrument to provide and measure those things. I found that there's two main types of equipment I like to use for that. There's the USB controlled instruments like the USB oscilloscopes, such as the Analog Discovery series from Digilent. USB controlled instruments are, you'll see like this, there's only the actual hardware on the bench. There's no screen, there's no way to control it in person here. The only way to control it is through a software GUI running on the computer that it's attached to. So that's a great way built in. And then the other option, the more traditional option that you'll run into in industry, are network controlled instruments that use a protocol called SCPI. SCPI is an acronym for Standard Commands for Programmable Instruments. It's a way to control devices such as power supplies, oscilloscopes, waveform generators, signal analyzers, all of the big fancy instruments you'll come across in industry as an electrical engineer. It's essentially just either over a serial COM port or a TCP/IP socket. You're just sending strings of commands in a certain format. Typically what that looks like is it's 4 letters delimited by colons and spaces. So for example, if you want to configure channel 1 of your power supply to output 5 volts, it'll be COF colon volt VOLT colon channel 1 space 5. Put that on the screen here. But that's a pretty common way, and most instruments will have something similar. So when you choose an instrument like this, it will come with a user guide that will show you all of the commands that are related to each action. So every button that you press on it has a corresponding SCPI command to execute it remotely. And then because it's a network connection, it's just a random socket that's opened. The user guide will also tell you which port the socket is on in the instrument. I have become really attached to this method because of everything. It's very robust and very simple to execute. So no matter what software I used, which we'll get into in a minute, I know that I can always open a socket, send it the string commands, and that's it. So if you are not familiar with SCPI commands, I would highly recommend picking up one of these instruments that have the SCPI interface, playing with it, getting to know it. This power supply I have here I got it on Amazon for about 250 bucks. I think you can buy it straight from the Signalit website for about 285. Great power supply, and then also it's a great way to practice and get familiar with those SCPI commands. I'll leave that link below. So I have my SCPI command controlled power supply to turn my whole setup off and on remotely. The other aspect to that is not only can I control it via the SCPI commands, I can also read the current back. That's a big deal because that kind of tells me A, is something wrong, and B, that'll give me a clue where things in my test setup, where they are in the boot process. That'll become important later as I go over through the whole setup. And then also, one of the telltale signs that things are about to go off the rails in a setup is your current might get wonky. So always reading the current of your setup and how much your target device is drawing is a big thing that I always recommend, not only in remotely controlled setups, but kind of setups in general. That's a long-winded explanation for why I choose to control it with a power supply versus having it plugged into like a wall wart on a power strip that I can turn off and on remotely, because that is another option in this. I haven't implemented it here, but they do make power strips like this where they have a little remote control, a little microcontroller in them that you can SSH into and turn plugs off and on individually. That has its time and its place, but I do recommend using a traditional power supply, especially with the price point of this power supply is reasonable enough. It's not that much crazier than a power strip that has that remote capability. But the more you know. So, going over my particular setup, some of you might recognize this particular test setup from previous project post. This is my test setup for my little direct digital synthesis chip. I bought this little blue board here is a development board for the AD9850 board. I have a Raspberry Pi Zero here running a Python script that provides the digital interface to the AD9850 chip that tells it which frequency to output. And then I have the output of the AD9850 going to my Analog Discovery 3 here, so I can verify its frequency output with the oscilloscope functionality of it. And I also have my ADP3450 connected to the digital output from the Raspberry Pi going to the 9850, so I can monitor that with the logic analyzer functionality. And the last part of this setup is the power supply is ultimately controlling the power going into the Raspberry Pi, which then the Raspberry Pi powers the AD9850. So because I have the power supply powering the Raspberry Pi Zero, what I can do is monitor the current draw of the Raspberry Pi Zero, which will tell me when the Raspberry Pi is fully booted up, when it's booted up its Wi-Fi chip, and when it's ready for me to SSH into it, which is how I'm controlling the Raspberry Pi Zero remotely. Is I have it configured so that I can SSH into it once it's booted up. In turn, when I give the power down command to the Raspberry Pi over the SSH, obviously it disconnects and I no longer have power to it. I can then monitor the current as well to see when it's fully shut down and it's safe to remove power, because I don't want to corrupt my image on the Raspberry Pi, because that, in this current setup, I don't have a way to change remotely. But we'll get in how to solve that later. So now that I've gone through my entire setup and how I've chosen the particular instruments I have, I also want to make note of how I've connected to them specifically. Pretty much any cable comes with a flying lead version, so that's what I chose for the Raspberry Pi since it's controlled by a micro USB. I found these micro USB to flying lead cables, which then allowed me to connect to it with my standard clip leads going back to my power supply. These particular cables were I think 15 bucks on Amazon, as well as a whole package of different test leads. So I recommend picking up some of these. You've got your standard banana to banana jacks, clip leads like I'm using here, and then also your alligator clips. Those are my 3 most frequently used type leads, along with my BNC scope probes. So these are what I would normally use with my ADP 3450, since I've got my scope and analog waveform generator here. The Analog Discovery 3 has the same functionality, except they come over the flying leads. Sometimes I like the probes a little bit better, just depends on the setup. The other thing is I'm a big fan of breadboards on remote setups, because that allows me to make multiple connections to the same point without making those connections permanent. I can move these around. So that's actually how I'm able to connect to the AD9850 with both the Raspberry Pi and the ADP 3450. Otherwise, I would just have these leads connected straight to it if I weren't trying to have these in the middle. And then as well as it gives me multiple ground points, because I have to have a common ground between power supply, target device, controller device, aka the Raspberry Pi Zero, and then my 2 USB controlled instruments. So that allowed me to pull out to a ground rail on a breadboard and have as many connections as I need. So now that I've covered hardware and a lot of the hardware I like to use, next is the software that we use to control all of this. So let's jump into that. So for the software to control your setup remotely, obviously you can do everything piecemeal by using the respective GUIs that come with your USB instruments. You can use just a plain old Python script that sends your SCPI commands straight to the socket, or a lot of modern instruments, like from Keysight or any of the other major brands, they have proprietary GUIs that come with them to kind of handle the SCPI commands in the background for you. But traditionally, or well, I say this traditionally as someone who used to be a test equipment engineer, typically you choose one software application to kind of control everything all in a centralized manner. And what I mean by that is you have a particular software program that has the drivers to talk to all of your instruments and the drivers to talk to a TCP socket, all within a centralized place, such that when you're creating your test sequences or creating your actual device test, it's all in one place. And furthermore, that software has 3 main elements to it. It has the actual capability to create the programs for signal processing, providing signal stimulus. It has some sort of sequencer to it, so each individual test, so like your power on versus your provide stimulus test versus your scope measurement test, each of those are compartmentalized, and then the sequencer runs each of those in the proper sequence. And then finally, a GUI element, so that it's easy to use, it's pretty, and it has a nice shiny on-off button. So not only does that make it easier for you to run your sequence, it is something you can ultimately hand off to a coworker for quality assurance, things like that. So some of the more typical software applications you'll see in industry that do this are NI's LabVIEW with Test Stand. LabVIEW is the software that actually creates each individual test. Test Stand is your sequencer that calls each VI, which is the little LabVIEW, each individual LabVIEW program you create. And then also you can create a VI that is a GUI, since they have all the GUI stuff in LabVIEW. MATLAB is another version of it. It's a little bit, I mean, you can create GUIs, you can create sequences, and then of course you write your underlying MATLAB scripts or Simulink models. I think that's a little bit tougher to use, but that's just from my experience. I come from that because I used MATLAB a lot in my undergrad, so that's why I defaulted to that initially. But there's another one I've come across recently called Daisy Lab, and unlike the spelling of our daisy flowers here, it's DASY Lab. Daisy Lab is very similar to, I would say, LabVIEW, from the sense that it's a more graphical drag and drop blocks and connect blocks type of thing. But unlike LabVIEW and Test Stand, where LabVIEW and Test Stand are separated as two separate software applications, the sequencer is built into Daisy Lab, along with the GUI, the same type of GUI stuff you can do in LabVIEW. I'm going to show you how I use Daisy Lab to create my test sequence to verify the output of my AD9850. It's the same setup where I tell it to output 1 megahertz. We're going to measure it to make sure that it's actually outputting 1 megahertz or close to 1 megahertz. So, starting with the first test in this setup is the power on sequence. So, like I said, I'm powering on the Raspberry Pi Zero using my power supply, and since the Raspberry Pi Zero, it's running a Linux image, I need to give it some time to boot up before the Wi-Fi chip is up and running and I can SSH into it. So the first thing I added here is the ICOM master, which allows Daisy Lab to talk to the socket of my power supply. The interface is the actual host IP address of my power supply with the particular port that power supply uses for its SCPI commands. I found this in its user guide, which for this particular device is 5025. I want to make note that this is not a standard thing that's common to every single device. Like I said, it just needs to be an open port that's not commonly used for other things like external traffic, port 80, or SSH port 22. So you always make sure to check the datasheet or user guide of your particular instrument. And then under transport protocol, I just choose other because it's none of these other things. It's just a plain old socket. And then for options, I have my start command as my actual SCPI command to set channel 1 of my power supply to 5 volts. Stop command, which is the command automatically issued by Daisy Lab when the whole measurement is stopped, is just to turn the channel off, even though it's already off. It's just a safe thing to do. And then the main measurement data request, which is the SCPI command that the ICOM master block is going to send the power supply continuously, is the actual query for the voltage setting. So that's this channel 1 : volt ? And then what I'm going to do is I'm going to output that. I have a little output display here so I can see what's going on. And just like LabVIEW, I have a stop button here, a stop execution for the whole program. And whenever the value gets to 5, it will stop the Daisy Lab program from executing. So as long as the SCPI command returns 5 volts, which is what it should be set to, my Daisy Lab program will stop executing, or worksheet. I'm still getting used to the Daisy Lab terminology. So that's our first test for this setup. The second test is the same thing, but to configure the current. So for a Raspberry Pi Zero, the maximum it should ever draw, well, should be no more than 2 amps ever. So I'm gonna set my power supply to 2 amps. That doesn't mean I'm driving 2 amps into my Raspberry Pi Zero. That just means the power supply will let the load, the Raspberry Pi Zero, draw up to 2 amps before it limits it at 2 amps. So again, I have the same setup in this program where I have the ICOM master. My initial start command is the command to set the current to 2 amps, and then it will continuously query it until the list here reads to back, which will ultimately stop the execution of the worksheet. So I could let this go on manually and also manually stop the worksheet if I wanted to, but because I'm going to put this in one big overall sequence, I do want to program in an automated mechanism for stopping the execution of the worksheet. So the next program in this test is once I have the power supply configured for the right voltage and current output, I actually need to turn it on. So I have this measure current. So what this does is on options for the start command, I have my output channel 1 on. That will actually turn on the channel output of my power supply to turn on the Raspberry Pi. Notice I have no stop command because I have that relegated to a different worksheet. This worksheet is solely meant to turn on the power supply. So that's why there's no stop command there. And then I will continually query the current again with this particular device. The only difference here being is my stop condition is now going to be the current level at which I know the Raspberry Pi Zero is on and its Wi-Fi chip is running. With some trial and error, I found that was about 2.5 amps or 250 milliamps. Once I hit that threshold, I know the Raspberry Pi is ready to go, the Wi-Fi chip's enabled, and I'm able to SSH into that. Again, that was some trial and error I found where I just continually, after I turned the Raspberry Pi on, I just continually pinged it while keeping an eye on the current draw until it finally let me ping it successfully. I made note of what that current draw was. So like I said, once the Raspberry Pi Zero reaches its operating current, the Daisy Lab worksheet will automatically stop execution. Which leads me to the main worksheet for this whole setup, which is the actual tester device. Oh, I opened the sequencer first. We'll get there. So for this test, what I'm doing is I have my actual analog input coming from the Analog Discovery 3, which is measuring the analog output from the DDS chip. I bring that in, and the first thing I do is I have that, just the raw output, dumping straight into a time domain scope screen. That way I can verify that I'm getting some sort of waveform is there. That's my first check. I then put it through a Fourier transform so I can view that same raw signal in the frequency domain. That way, when it's unfiltered, I can see everything. Are there any spurs? Are there any harmonics? I'm visually assessing this at this point. Is my center frequency anywhere close? This other further processing thing, I'm also applying the equivalent of a peak hold on an oscilloscope. So that's what this block average is doing, is it's taking each individual peak measurement here, which is what the FFT max operation is doing, is it's measuring the max amplitude peak it finds and then outputting that as a discrete value. So I have that here, which is just each individual running thing, and then putting it through the block average, which I chose continuous peak hold. And then that's my unfiltered raw input from my DDS. I'm then putting it through a bandpass filter to look in the specific bandwidth of the frequency I told it to output. So in this case, I'm telling the DDS to output a 1 megahertz signal. So I have a bandpass filter here going from 500 kilohertz to 1.5 megahertz. And hopefully my output is somewhere in the middle there, otherwise, not good. So, same thing from there. I have that going through. A thing to note about Daisy Lab here is the filtering is actually done in the time domain, so I do need to put that through an FFT again, move that over to the frequency domain. I'm looking at the actual frequency, the filtered frequency domain on this graph, and then again applying my same peak hold measurement so I can see what is the actual frequency the DDS chip is outputting, because pretty much with any RF output like that, you're going to have some sort of minor, should be minor, deviation from what you actually commanded it to do. So, for instance, I probably won't get exactly 1 megahertz. I'll probably get 999, 998, or a few hertz on the other side. But that's what this graph is going to show me. And then I also have a start and stop switch. So because I want this to run continuously so that I can send different values from the Raspberry Pi to the DDS chip, I want to control when the worksheet stops executing. But because it's going to be in an overall sequence, I can't just manually hit the start stop button, or I could, but that gets messy. So I've also added an on-off switch, which this is a great segue into the GUI functionality of DAISY Lab. Those of you that are familiar with LabVIEW, this will look familiar. It's a little bit different in the way that you add buttons and relate them back to specific things in, I keep wanting to say flow graph, but it's the worksheet. Old habits die hard. Overall, very, very handy. So as you can see, the view has cleaned up quite a bit. Instead of kind of having the chaos, I have one nice pretty thing. I can add all my pretty text. And then also it kind of works as built-in documentation as well. And finally, I have one last worksheet. So running separately from this, I do also have a terminal open over here, which I will use to actually SSH into the Raspberry Pi. I don't have that built into the LabVIEW worksheet. I want that separate since I have manual control over it, since I want to change how often I send the script to reconfigure the DDS output frequency. The other thing I have separately is, so while the Analog Discovery 3 is being controlled within DAISY Lab, I do have my ADP 3450 with the logic analyzer function. That's running separate in waveforms. Not that DAISY Lab can't handle driving both at the same time. It's just because for the same reason that I'm running the Raspberry Pi manually, because I want to control how often I'm changing the DDS output frequency. Because this is measuring the digital interface, this also needs to be manual in step with that. So yeah, this logic analyzer is validating what the Raspberry Pi is outputting. So that does two things. I can prove in the script that I'm writing to drive the digital input of the AD9850, which did take a little bit of trial and error because it has an SCPI interface that's a little bit unique. So the logic analyzer was very key in figuring out how to get my script to match what the AD9850 datasheet called it out for its digital interface. And then also DAISY Lab is, or well, not DAISY Lab itself, but the actual drivers for the analog discovery devices don't have the logic analyzer function built into them. The specific Digilant drivers in DAISY Lab are in the beta phase right now, but I do expect that to change soon. They've revamped it this year, so I expect lots of updates there, but hopefully I'll be the first to know. Now that I've explained my whole setup, the flow, let's take a look at the sequence and actually run it so you can see it in action. So in the sequencer in DAISY Lab, I've called out each of my individual programs. I have my starting worksheet, which is the one that configures the voltage on the power supply, followed by the worksheet that configures the current, configures and validates, followed by the current measurement worksheet that turns on the power supply and then measures the current until the Raspberry Pi Zero reaches its operating current, at which point it launches my final main tester worksheet, which is monitoring the analog output from the AD9850. Once that is running, it just gives me a live output, and then I can switch over to my serial terminal to SSH into the Raspberry Pi, and also switch over to waveforms to view my ILA. So let's run this. Before I run it, let me double check that I've had trouble with this particular power supply changing IP addresses on me, even though I have DHCP turned off, which, okay. Of course, now that I said it would do it, it didn't do it. But, oh, this is, I think I forgot to cover this as well. When you're setting up the bench before you leave it remotely, I highly recommend turning off DHCP. Otherwise, when you're on your remote PC, you'll have to query the network, the local network of your remote setup every time to figure out what DHCP might have changed it to. So yes, always turn DHCP off. DHCP is kind of your enemy in remote setups because you don't want anything changing, since you do have to hard code it to some extent in all of your worksheets. I suppose the smarter thing to do would make a global variable so that if it does change, I just change the one variable. But anyway, I will stop rambling. Let's run the worksheet. So if I go ahead, if I want to run the sequence, I'll hit run from the sequence window. Yeah, I hate that it always thinks something's been modified even though I just opened it. So we have voltage, it's querying the voltage. Now it's going to move on to configuring the current. And now we are turning on the power supply and monitoring the current draw of the Raspberry Pi Zero. So we're going to let this power up for a minute. Even though I can lean over and look at it here, that's why I have the list here, so I can look at it, get an idea of where I'm at in the process. This does take a couple minutes. Almost there. Hit 2.5, so we're going to switch over to the main sheet. You can see we're running here. Interesting, even though I haven't enabled it, it looks like I have some sort of, this is probably leakage from the onboard oscillator on the DDS dev board, since the center of this is 1 megahertz and the onboard oscillator driving the chip, the DDS chip, is 25 was it 25 or what was it? Can't remember. This seems to be right about where it is. So I'm going to switch over to my serial terminal. And I'm just going to ping the Raspberry Pi just to double check. And fun hack, instead of trying to figure out what specific IP address my Raspberry Pi Zero got assigned, I can just ping raspberrypi.local. So that does require you to be on the computer that's connected to the same local area network or remoting into that computer. So now that I know that my Raspberry Pi indeed is up and running, let's SSH into it, to my user, and I can do the same Raspberry Pi.local, or the IP address, doesn't matter, whichever you want to use. Enter password. So now that I'm logged into my Raspberry Pi, let's run the script to, or we'll queue it up because I need to switch back to waveforms. And so there is my script that is going to tell the DDS chip to output 1 megahertz. So I do have waveforms ready to go here. I have the logic analyzer configured to look at an SCPI protocol and trigger off the start of an SCPI protocol. So I've got it over here to where, oh, I should skip to my, let me switch to my actual GUI window because that's kind of the point of it, my nice pretty GUI window. And then have waveforms up and kind of see both of them going here. And we'll send the command run my script. Oh, it helps. Helps if I hit run on my trigger. That's okay, it's already outputting. I'll just tell it to output the same 1 megahertz again. That's what my script's hard coded to. There we go. So as you can see, I captured my SCPI protocol, and then looking at my GUI back here, I successfully am outputting 1 megahertz. Well, almost. I'm honestly amazed this little DDS development board works at all. As you can see, the longer I run it, the closer it'll get to my 1 megahertz. Initially, it's pretty far off. I'm only at 865 kilohertz. This was a cool little dev board I bought off of, I think, Amazon again. There's lots of things I can buy on Amazon. That's dangerous. It showed up in a Ziploc bag, not an ESD bag, a Ziploc bag in styrofoam. I can't think of, if you asked me to purposely try to kill something with ESD, I couldn't think of a better thing to use than styrofoam. But Ziploc bag is, so I have to give it props. However, the circuit's design has good ESD protection, but only so much so. I'm still at 800 on my center frequency peak hold here. I'm still only at 865 kilohertz instead of my 1 megahertz. So obviously this would not be an acceptable device to use in any endpoint application, but you can see how my test setup has told me as such. So now that I've viewed my entire test setup, so again, looking at this, I have my raw time domain output validating that I'm actually indeed getting some sort of output. I have my raw unfiltered output, which it looks like I have some something causing a pretty high peak at 1.82 kilohertz, which is even further away from what I told it. And then once I filter around that to get rid of it, oh, you can see we're slightly starting to go up. As the DDS compiler or DDS chip warms up, I'm getting closer to 1 megahertz. Usually it's the last few times I've run this test, it usually gets to about 960 kilohertz. I haven't seen it take this long to get close to 1 megahertz before. But unfiltered, filtered output, and that's my remote test setup. So as you can see, aside from double checking the IP address of my power supply, I touched none of my hardware once it was set up to run this entire sequence. I have my nice pretty GUI, and that's how you could create a remote benchtop setup for remote, and I've said remote too many times, and automated test setups. This is a big thing when you're developing any sort of product. You do want to have some sort of automated tester. Like I said, if you're going to hand everything off to your QA or even just a technician to run, a nice pretty GUI with a nice pretty off button is great to have. And there we go, we've powered it off. And then I can come back to my Raspberry Pi and shut it down safely. And actually I'm gonna hold off to run that real quick because I do want to come back to, let me open my worksheet to power off. So this is the same thing. It'll monitor the skip, it'll read back the current of my power supply to see when the Raspberry Pi is actually shut off. So if I go ahead and run this. So I have noticed there is some sort of underlying memory leak or process issue in this particular version of Daisy Lab. I know there's an update coming soon. I somehow have triggered that in this, of course, but I'll just go ahead and shut down my Raspberry Pi, always shut down safely. Daisy Lab is very similar to some other stuff like LabVIEW in market. I will say LabVIEW is kind of like a big brother to Daisy Lab in terms of functionality. There's a lot more, Daisy Lab does a lot in terms of base functionality, but some of the more complex signal processing, DSP type stuff, some of those blocks you would want to upgrade to LabVIEW. Consequentially, Daisy Lab has a lower price point than LabVIEW. So if we take a look at Daisy Lab pricing, you have Lite, Basic, and Pro. Pro, you can buy 2,500, gets you a perpetual permanent license. Licenses like that, when they're perpetual, tie themselves to your computer's MAC ID or the ID of your hard drive. So if you do choose a perpetual license of anything, LabVIEW has the same perpetual license option. Just be aware of the fact that, say your computer dies or you upgrade your computer, your license is no longer going to work. It is fixable. Just reach out to the support of whoever, whether it be NI or Digilant or whoever, and just say, hey, I changed computers. They'll issue a new license for the new ID. That's typically how that works. Daisy Lab kind of gives you different tiers. So some of the lower price points, there's less modules you have access to. And then LabVIEW, as you can see, prices are definitely higher. But like I said, it is a little bit more beefy of a tool in terms of more complex processing blocks. So hopefully that will help you decide which one you want. Daisy Lab is honestly, as you can see, I made a pretty all-encompassing test setup very easily. As someone that has a LabVIEW background and is familiar with LabVIEW and Test Stand, it probably took me about an hour to adjust and acquaint myself to Daisy Lab and get up and going with it. So very similar. I think it's a great lower cost alternative when you don't need all the fanciness of LabVIEW. And you may not be familiar with MATLAB, which has a higher price point and is a little bit more complex to get everything situated. But again, that has its time and a place. I hope this was helpful. Let me know. I'm sure that I've either missed things or spawned more questions. Let me know if you have gotten anything from this, have any further questions. Were you familiar with SCPI commands before this video? I'm surprised that a lot of my fellow engineers I've come across, if they didn't have a past life of being a test equipment engineer, have not used SCPI commands before, so I don't know if maybe I'm biased in thinking that's more widely used. I'm not sure. Let me know what you think. I will also have all relevant project links, like past project links explaining in more depth the DDS compiler, how I developed the script for its digital input to tell it which frequency to output. I'll have tutorial scripts on everything else, and then also stay tuned for a getting started with Daisy Lab tutorial, because I just showed you the cool things and not how to make those cool things specifically. So I think I've rambled on enough. Like I said, let me know what you think in the comments below, and I will catch you in the next video. Bye!